Hi, folks. In this last section of Chapter 8, we are going to kind of compile together things that we've learned in a few different previous chapters. The first types of equations we learned about were linear functions. And then this semester, we started learning about exponential functions. And then more recently, we've started learning about quadratic functions. So we're going to look at all of these together to make sure that we know how they're different from each other, how we can tell them apart. And one way that we're going to compare these functions to each other is by looking at an average rate of change. And the average rate of change is kind of like calculating the slope of a line. It's going to be the change in y divided by the change in x. But you can do an average rate of change for any kind of function, not just a straight line. And so we'll look at that in a moment. But for now, just look at these three different types of graphs. If you have a linear function, that's going to be a straight line. An exponential function, it has a curve that approaches an asymptote um, uh, on one end and then goes to infinity on the other end. And then quadratic functions are a U-shaped graph. And look at the difference in the functions themselves. In a linear function, your x, your variable, is only raised to the first power. There's no kind of squared or cubed or anything like that on the variable. In an exponential function, the x is actually an exponent itself. So it's not that x is raised to a power, it is that x is the power on an exponential function. And then in a quadratic function, the largest exponent on your variable is a 2. You have to have a 2 as an exponent on the variable. So let's use that information and try to identify the difference between exponential, quadratic, linear functions. In this first example, we're asked to just plot some points and decide whether the graphs appear to represent linear, exponential, or quadratic functions. So again, pausing the video, making sure that you've got the kind of points and the same answers that I have. For graph A, we want to have a point at 4, 4, 2, 0, 0, 0, 1, -1/2, and -2, 4. So this definitely appears to be a U-shape parabola. So this would be a quadratic function. The next set of points given, I have a point at 0, 1, 2, 4, 4, 7, which doesn't actually fit on this graph. -2, 2. I'm sorry, -2, -2. And then -4, 5, -5. And this is definitely a straight line. So this is a linear function. And then lastly, we have points at 0, 2, 2, 8, which doesn't fit on this graph, 1, 4, -1, 1, and -2, 1/2. This appears to be approaching the y equals 0 on the left side, approaches an asymptote, and extends to infinity as we move to positive values of x. So this is an exponential function. So just being able to recognize those different shapes is an important skill. What if we don't have graphs? What if we just look at data tables? Is there a way to tell the difference between the different types of functions here? And the answer is yes. Some of these differences we've learned about before. First of all, if you have a common difference, if you're consistently adding or subtracting by the same value, in this case, we seem to be subtracting 3 every single time. Now, it is important. Do check the x values. If there's no pattern in the x values, then you can't expect a pattern in the y value. So just confirm that the y values are doing the x values are doing something consistent. Here we seem to be consistently adding 1, adding 1, adding 1. So in this example, we have a common difference. Common difference is -3. Therefore, this is a linear function. Okay. Next example. Here, what seems to be happening, first, let's check the x values. I'm increasing by 1, increasing by 1, increasing by 1, increasing by 1. So yes, there's a regular pattern to my x values. Let's look at what's happening with the y values. Maybe I'm adding 1. Okay, I'm definitely not adding 1. I seem to be multiplying by 2. So here we have a common ratio. The common ratio is times 2. And so this is going to be an exponential function. If you're consistently multiplying by the same value, that does give you a common ratio, which lets you know that you have an exponential function. In this last example, we are looking for a pattern. Again, is there anything consistent happening with the x values? Yes, we're constantly adding 1. So now we can look for a pattern in the y values. Here, let's see, I seem to be -1, then -2, then -1. I'm not multiplying by anything or dividing. I'm not adding or subtracting by anything. But yet, I'm still going to write down what the common difference is. Not a common difference, but what the difference is in each step. So here I seem to be subtracting 1. And then here I seem to be adding 1. And here I seem to be adding 3. And here I seem to be adding 5. There doesn't seem to be a consistent pattern here, but the trick with quadratic functions is that they don't have a common difference, but they have a common second difference. So what you need to do is you need to check to see if there's a common difference. And then you take that one step further and you see if there isn't a common difference, but so you then check to see if there's a common second difference. So going from -1 to +1, that is adding 2. Going from 1 to 3, that's adding 2. Going from 3 to 5 is adding 2. So quadratic functions have a common second difference. Common second difference of +2. And therefore, this is a quadratic function. So just as a reminder, our linear functions have a common difference, that value that you add to get to the next term. That's what we saw in example A. Then our exponential functions have a common ratio. You're multiplying by a consistent value to get the next term in the sequence, like we have in example B. And then lastly, quadratic functions have a common second difference. So we've found ways to differentiate between the functions if we have graphs or if we have data tables. What do we need to be able to, what else do we need to be able to do with these different types of functions? We might be asked to write a function that models the data. Writing a function that models the data. So here we've got a data table. I don't know if it's exponential, if it's linear, if it's quadratic. So I need to check what's happening with the between different terms in the kind of sequence that I've got here. It appears that with the x values, I'm consistently adding 1. So I do have a recognizable pattern here with my x values. And then with the y values, let's see, the numbers seem to be going down and then back up. So there's not a multiplication factor here. Um, let's see, adding or subtracting. Let's say I'm subtracting 12, then I'm subtracting 4, then I'm adding 4, and then I'm adding 12. So there's not a common ratio and there's not a common difference. So I'm going to check for that second difference and see if there's a common second difference. Here I'm adding 8. Here I'm adding 8. And here I'm adding 8. So this is a quadratic function. So I want to write an equation for a quadratic function that matches these data. It would help if I knew the vertex, or it would help if I knew what the zeros were. And as it turns out, I do know what the zeros are because x is 1 when y equals 0, and x is 3 when y equals 0. So I can use intercept form to help me write the function. I can use intercept form, which looks like f of x equals a times x minus p times x minus q. So I'm going to plug in values for p and for q. My p value is 1 and my q value is 3. I still don't know what my a value is, but this has gotten me started on the function. Now, in order to figure out the a value, I need to pick another point that's on the parabola. And it's my choice. You know what? I'm going to choose 0, 12 because having zeros in the equation often makes it easier to solve. So I'm going to plug 12 in for my y value, my f of x value. I'm going to plug in 0 for my x value. And the rest of my equation will stay the same. I'll subtract 1 here and I'll subtract 3 here. And I'll end up with 12 equals a times, this is negative 1 and this is negative 3. So I now, negative 1 times negative 3 is positive 3. So 3a equals 12, which of course means that a equals 4. I know my a value now. So I can take this version of the equation that I wrote before and combine it with what I know about a now to write a new function or a complete function, f of x equals 4 times x minus 1 times x minus 3. It wasn't actually stated whether I needed to write this in standard form or not, but it's good practice to try to write it in standard form. So I'm going to leave my 4 outside the parentheses for now, and I'm going to multiply the two polynomials together. X times x is x squared. X times negative 3 is negative 3x. Negative 1 times x is negative x. And negative 1 times negative 3 is positive 3. So I'll have, when I combine the like terms, I'll have x squared minus 4x plus 3. And now if I just distribute that 4 onto each term inside parentheses, I end up with 4x squared minus 16x plus 12. And that is my final function for the quadratic equation that models these data. The next question is asking us to write a recursive rule for this quadratic function. We've already written an explicit rule where we can just plug in any value that we want to for x and get an answer. But we want to come up with a recursive rule where we kind of have a starting term. And in fact, you always need to give a starting value for a recursive function. So starting with f of 0 seems like a good place to start. F of 0, as we see here in red, is 12. So I'm giving you the starting term, and now we want to get each subsequent term by building off of that previous term. This is a bit complicated for a quadratic function because it's going to be a two-step process, just like we had to kind of look for a common second difference. This is going to be a two-step process for coming up with this recursive rule. The first step, besides just giving a starting value, is to write an explicit rule for the nth term of the sequence of first differences. That means I want to use these numbers here to help me figure out how to get this sequence of green numbers. This is a linear pattern because I'm constantly adding 8 to get the next green term in the sequence. So I'm going to write my arithmetic sequence function, which just looks like the nth term in an arithmetic linear sequence is the first term plus n minus 1 times d, the common difference. I know that my first term in that green sequence is negative 12. And I know that my d, my common difference, is because of my blue sequence, is 8. And so I can leave the rest of the function as is. Oops, I was going to write that in red. N minus 1 times the 8, and I can leave this here as well. So I have now written an arithmetic, an explicit arithmetic rule for getting the next term in the sequence. I am going to simplify this a bit so I don't have parentheses anymore. I'll write this as negative 12 plus 8n minus 8. And I've got some like terms here that I can combine. So I'll have 8n minus 20. So I finished step 2. I've written that explicit rule for the nth term of the sequence of first differences. Now I'm going to add the expression that I just wrote down from step 2 to the previous term to get the next term in the sequence. So recursive rules work this way. You get the next term in the sequence by taking the previous term and adding something to it. But that something that I'm adding to it is this whole equation that or this whole expression that we've just figured out, the 8n minus 20. So I end up with taking the previous term, adding 8n minus 20. I didn't really need to rewrite it down. But this is how you write a recursive rule for a quadratic function. All right. More importantly than being able to write that recursive rule is using and interpreting average rates of change. I mentioned at the start that this was basically like calculating the slope of a line, but it doesn't need to be a straight line to want to calculate this average rate of change. Here I've got two networks that with their membership numbers. I've got actual numbers in this data table for network A, and then I've got a graph of members in network B. And I want to compare the rates, the rate of change from day 10 to day 20. I'm finding how quickly those numbers changed there to what I see on this graph here, going from day 10 to day 20. So to calculate that rate of change, you do the change in y over the change in x. So the change in y for network A is 2150 minus 1400. So you do the later value minus the earlier value over 20 minus 10. So the change in y values divided by the change in x values. Well, that gives me 750 divided by 10, which works out to be 75 members per day is my rate of change. So network A is gaining about 75 members per day over this particular time span. I'm not necessarily saying that this um, network keeps that forever, but in that time span between day 10 and day 20, that's the average rate of change. If I look over here at this other graph, my data points appear to be at 10 comma 900 and at 20 comma 1800. So using those numbers, once again, change in y divided by change in x. The change in y is 1800 minus 900, and the change in x is 20 minus 10, and that gives us 900 divided by 10, which is 90. And again, this is in members per day. So if we compare those two numbers over this particular time span, network B has a higher rate of change, is gaining more new members per day than network A. Network B gets more new members per day on this time scale anyway. Now, one thing to realize is that depending on the kind of graph you have, linear versus exponential versus quadratic, that does affect how the rate of change changes over time. So, over time, the average rate of change for linear stays uh, it will be lower than a quadratic function, and a quadratic function will be lower than an exponential function. So if you let time go on and on and on for long enough, the linear rate of change will always end up being less than the quadratic rate of change, and that will always end up being less than the exponential rate of change. It may take a while to achieve those differences, but eventually those differences will appear. So, for instance, if we've got sea turtle nests on an island versus a wildlife refuge, we've got this function representing the number of sea turtle nests counted on the island. And we're talking about years after 1990. And then the wildlife refuge has 1,275 nests, and the number is increasing by 6% each year. So what I have here is I have a quadratic function. This is going to be one of those parabola-shaped graphs. Um, a quadratic function because of that squared term on the x. And over here, the function that I have for the refuge, I start with 1,275 nests, but I grow by 6% each year. This is a description of an exponential function. So exponential functions have that format, or this is particularly a growth function, is going to have the format y equals some base rate times 1 plus the growth rate raised to the t power or the x power. So I'm going to start with 1,275 nests, and I've got to add 6%, and 6% is 0.06 raised to the t power. Given that I have an exponential function here, but a quadratic function over here, if I wait long enough, the wildlife refuge, the exponential function, will have the larger growth rate. So the refuge will have the greater number of nests because it is an exponential function. But that doesn't mean that right now, between 1990 and 2010, with the question that we were being asked, that doesn't mean that the island might not be beating out the wildlife refuge for small values of x. So just because eventually the exponential function will win doesn't mean that the exponential function is winning right now. In order to find out who's winning right now, we need to test values between, we need to find out the average rate of change between 1990 and 2010. And remember, our X represents the years after 1990. So I want to know the scale from between when X equals 0 to when X equals 20, because I want to do 20 years after 1990. So we'll go ahead and calculate that. We'll calculate L of 0 and L of 20 for the island. And if I plug 0 in here, I get 4 times 0 squared plus 72 times 0 plus 1750. And I get 1750 from that one. And then in year 20, I get 4 times 20 squared plus 72 times 20 plus 1750. And this one's going to take a couple of extra steps. I'll do this in my calculator and I get 4,790. So to calculate my rate of change, I'll subtract my y values, 4,790 minus 1,750, and I'll divide by the difference in x values, the 20 minus 0, and I end up with 3,040 divided by 20, which is 152. Oops. 152 is my average rate of change, the number of turtle nests per year. Let's do a similar calculation for my wildlife refuge. Maybe I'll call this W of X here for my wildlife refuge. Again, I want to plug in the number 0 and the number 20 for my X values. So when I plug in the number 0, I'll have 1,275 times 1.06 raised to the 0th power. Well, any number raised to the 0th power is just 1, so I'm going to end up with 1,275 nests in year 0. And then in year 20, I'll do 1,275 times 1.06 to the 20th power, and I get 4,089. To calculate this rate of change, I do the difference in y values, 4,089 minus 1,275, over the change in x values, 20 minus 0, and you get 2,814 over 20, which is 140.7. This is new turtle nests per year over that time span. We can see from doing the calculations that in fact the island has the greater rate of change, greater average rate of change, because calculating that average rate of change gave a higher value for the island than it did for the wildlife reserve. However, remember, over time, because the refuge has exponential growth and the island only has quadratic growth, that eventually the refuge will overtake the island and have a faster rate of growth. I hope this helped.